Hi everyone, in this video we are going to discuss solubility in the context of salt water. So we've already discussed pure water, fresh water, and we've also discussed a little bit about salt water. We know that our planet is made up of 97% salt water, but really that's all we've said. And so what we want to do with this video is try to see if we can have a microscopic view of salt water. So let's start off with a macroscopic view because that one's a little bit easier to visualize. So we have macro here first. And so we're going to take something like sodium chloride, right? Think about our ocean. Sodium chloride or salt, and we're going to dissolve it into water. Now, on a macroscopic level, all we can say is that we know that our ionic compound is going to dissociate into its respective ions. And so we're going to have our sodium cation, and that's going to be in the aqueous phase. And then we have our chlorine anion, which is also going to be in the aqueous phase. So right now what I can see is that my system goes from solid on the reactant side to aqueous on my product side, all because I've dissolved something in water. But realistically, that doesn't give us a great visual of what's going on. In my mind, when I see that, it's just like, oh, okay, a bond was broken. But realistically, that's not what happens at all. So what I'm going to do is give myself a little bit more space so I can kind of draw this out for you. So what we have is we know that sodium chloride is actually existent in a lattice, okay? Whoopsies. So it exists in a lattice, and so what happens is instead of having just one sodium for every chlorine, we know that there's actually this huge lattice of alternating units, so every other corner is either a sodium or a chloride. So it goes sodium, chlorine, so on and so forth. So it's this huge, strong lattice. Now when we put that lattice into water, that component hasn't changed, it's still just an arrow. Two very unique things happen. And so the first thing that happens is we try to kind of break each one of these pieces apart into its respective ions like before. So we have a sodium plus, I'm just going to focus on sodium right here. So what I see with my sodium is I know that that is a full positive charge, and we've now dissolved that into water. And so we know from previous videos that if we draw water out, it has a bent geometry with a partial negative charge over the most electronegative atom in this molecule, or second most electronegative overall. And then we know that we have partial positives over our hydrogen atoms. So what happens when we dissolve this lattice into water, we basically have several different water molecules that immediately are attracted to that positive charge. But because water is polar, only one side of it is attracted to that side. So what happens is the water comes and it tries to surround the positive charge, the cation, with as much negative as it possibly can. So it's going to do everything it can to surround the sodium with the oxygen side of the water molecules. And you have to remember that the hydrogen atoms are going to be as super negative, I mean relatively, it's partially positive, and so they're going to be as far away from that positive charge as possible. They do not want to be near that positive charge. And so what happens is just hundreds of water molecules surround the sodium, and you just try to balance out the charge. Now what's really neat about this is called an ion, so sodium being the ion, and then dipole because our water molecules are polar. So this interaction right here is another intermolecular force, so not hydrogen bonding, but this one is called an ion-dipole interaction, and it's incredibly strong. Significantly weaker than hydrogen bonding, but it is incredibly strong. Now, if that's what happens with the sodium ions, let's see what happens to the chlorine ions. So instead, with our chlorine anion, it's negative. And so instead of trying to put the oxygen next to the chlorine, that's not what's going to happen at all. Instead, now these water molecules are going to orient themselves so that the partial positive charges on the hydrogens are as close to that chlorine as possible. And so again, you're trying to balance out that charge. And just like with the sodium, we have the same ion-dipole intermolecular force going on. And so that's how this works, or what it actually looks like on a microscopic level. So if you picture the ocean, or you picture your pasta water that you're trying to boil and you've added a little salt to it, this is really what's going on. You have all these really neat ions there, and they're surrounded by so many water molecules in every direction, in every axis, and they've just oriented themselves so that any chlorine or any negative, so an anion, is going to be attracted to the positive side of the water molecule, so the hydrogen, whereas any cations that are dissolved in water are going to be attracted to the oxygen side of the water molecule. So it's really cool. It's so cool. And so this is actually what happens in real life in salt water, and it's just neat. I love it. So now, how are you supposed to know what actually dissolves in water and what doesn't? Because some molecules do, some ions don't. It just totally depends on the specific ion. So what I'm going to do here is give you a really short list that I personally would become very familiar with if it was up to me. So the first thing I want you to do is understand that all of these species that I have in this chart, so just the 4 of them, are always soluble in water. And this is for water. I want to be very clear about this. Chart's always only for water. If you change your solvent, the solubility rules completely change. So in water, if you dissolve sodium plus or potassium plus or NH4 cation or NO3 anion, they will always dissolve. Okay, so your sodium, potassium, ammonium, and nitrate are always soluble. Then we also have a category called mostly soluble. In our mostly soluble category, we just have 2 species. We have our chlorine anion and we have our sulfate anion. And so these 2 species are mostly soluble. So for our course, if you ever see any of these 6 anions or cations, you should just automatically assume they're going to dissolve in water. Just for our course, they're going to dissolve. These 2, there are some exceptions, obviously, but we're just going to, for our course, say chlorine sulfate that always goes in water. Now, the last one is going to be our insoluble chart. So for our course, we know that these 3 anions, yep, they're all anions, are never going to dissolve in water. So the first one is going to be carbonate. Carbonate is basically limestone. Limestone doesn't dissolve in water. That's just a rock, and it just sits in the bottom of water. So carbonate, definitely insoluble, not going to dissolve in water. The other one we have is our hydroxide ion, or OH minus, and then our sulfide ion, so S2 minus. So all 3 of these are never going to dissolve in water. So if I ask you, is something hydroxide going to dissolve, you're automatically going to go no, because I know it's insoluble. So let me ask you some questions. Will calcium carbonate dissolve in water? Go. All right, did you say no? Hopefully you said no, because what you can see right here is that in our insoluble list we have carbonate, and so we know for sure that anytime you have carbonate, it's not going to dissolve in water, so that's definitely no. How about calcium chloride? Will calcium chloride dissolve in water? All right, did you get an answer? Hopefully you did, and the first thing I would have done is looked at both my cation and my anion. So the first thing I see is my potassium is definitely soluble, so we're good here. Then I look for my chlorine. I see that my chlorine is in a mostly soluble list. So for this course, anytime you would dissolve KCl in water, I would say it's definitely going to dissolve, definitely soluble. All right, last 2 questions right here. If I dissolve calcium chloride into water, is my potassium section going to be attracted to my oxygen or my hydrogen? I'm also going to ask you for chlorine as well. Go. All right, did you get an answer? Hopefully you did. All you had to do was identify it. Is it a cation or an anion? So the first thing I would say is my potassium is definitely going to have a +1 charge. It's positive, so the only thing that's going to be attracted to it is going to be the oxygen component that is negative in in water, okay? So the oxygen is going to be attracted to the potassium. Now for chlorine, it's going to be the exact opposite. We know chlorine's an anion. It has a negative charge, and so since it has a negative charge, we definitely know that the hydrogens in the water that have a partially positive charge are going to be attracted to the chlorine. And so just so you can have a visual representation of this is how I drew it out personally. I always use 4 water molecules, but that's completely arbitrary. You can decide how many you want to use. The big thing is that you just need to draw your potassium and have that plus charge. And then what I would do is make sure that you're very clear that the oxygen has a partially negative charge and there is a very, very strong ion-dipole interaction going on from the water to that potassium charge. So let me write this out. Ion dipole interaction. That's what I keep saying. All right, so now the chlorine, same thing. It has a -1 charge, and so we know that the water is going to orient itself around so that all of the positives, so all of the hydrogens are going to be as close to the chlorine as possible to try to cancel out or balance that charge. All right, same thing, very strong ion dipole interaction. That's it. That's all I have for you today. Take care of yourself. Drink water.